Hello everyone, hope you're doing good. Welcome back to my channel. Today we are at day 24 of the October Daily Leetcode Challenge, and we again have a question around trees. Okay, yesterday also that is on day 23 of the October Daily Leetcode Challenge. Again we had question on trees, and this is on a similar topic. That is, it's also on trees, but here the approach will be slightly different compared to what we had previously. In yesterday's solution, we were trying the DFS approach. Basically, from the parent we were trying to change the values. That is, we were trying to get the values of the child nodes, and yeah, there we also had the concept of a cousin node, what a cousin node is, and we had a question on that particular, these topics, revolving around these topics. Okay, traversal, and then how to access the value of the child node from the parent node, and how to do it in such a way that it doesn't affect the the logic for the other child nodes. As simple as that. That was the basic idea in that. But in today's question, it's slightly different. It's really interesting. Basically, once you get to know it, once you solve it, you will really feel a bit, you will feel like you are on top of your top of your skills, because this is something like that. Okay, though you are very good in topics like trees and other rough, like other topics, but still I am damn sure you will find it difficult to solve this kind of questions, because here the logic is slightly different. Okay, so pay your full attention here. Let's see how it works. It's question 951. Flip equivalent binary trees. Okay, here we are having binary trees. As the question name suggests, there is something called equivalent, and also there is something called a flipping operation. Okay, we'll see that. Okay, for a binary tree, we can define a flip operation as follows. Okay, choose any node and swap the left and the right child subtrees. Okay, take any node, swap its child. That is, the left subtree will come to its right, the right subtree will come to its left. Okay, that is what is called a flip operation. Okay, and remember, it can be done on any node. It can be done on any node. It's not a not something like it has to be done like on all the nodes, or it should not be on any node, nothing like that. It can be done on any node. Okay, that is the basic idea of flip operation. A binary tree X is a flip equivalent of a binary tree Y if and only if we can make X equal to Y after some number of flip operations. Remember, again, same thing. They are saying some number of flip operations. Okay, they are not mandating it that all the nodes should be flipped or something like that. They are simply saying we can flip some nodes, we need not flip some nodes, but you have to tell that whether X is a flip equivalent of Y or not. Okay, given the roots of the given the roots of two binary trees, root 4 and root 2, return true if the two trees are flip equivalent, otherwise return false. So let us quickly jump into this particular question. So if you see, we'll compare for each node. Okay, we'll compare node by node. That is, when I'm at a particular node, I will compare its child and we'll decide whether it is flipped or not. Okay, so by the way, but the answer for this is true. That is, they are flip equivalent. So we'll try to see how they are flip equivalent. Okay, this is the first example. If I consider the parent one, okay, that is the node one, I'm considering it as a parent. So let us see based on that if it is flip equivalent or not. See, 2 and 3. 2 is at the left and 3 is at the right. Okay. Here we are simply flipping it. Okay. 3 is coming to the right and now 2 is at the left. Okay. There's a flip equivalent in terms of parent one. Okay. Now, let us consider 2. What is happening to 2? 2 has the childs in the order 4 and 5. Okay. Here also 2 has the order childs in the order 4 and 5. Here there is no flipping happening. Okay. See it very clearly. Here there is no flipping happening. Okay. Now coming to 3. 3 has only a one child which is in the left. Here 3 has only one child which is in the right. Here the flipping is happening. Similarly, 4 does not have any childs. That is fine. Come to 5. 5 has childs in the order 7 and 8. Similarly, here 5 has childs in the order 8 and 7. So here also a flip is happening. So now the question is how you will be comparing them. See, there are many ways to do it. Okay, but I will tell you the one which makes sense to me the most. Okay, see, there are many ways you can do brute force approach, and you can try many things. It may work, it may not work. That difficult here is because see the traversals, the DFS, the BFS, those obviously here you will be trying for the DFS only, not the BFS. But yeah, even in those traversals it will be slightly difficult, because for example, see the case of this here 3 does not have a child. It has only single child which is in the left. Similarly here we are flipping it this, now it is coming to the right, so the other child will be none. So how to do the traverse in this case such that you are not traversing on an empty node, and calling it as the dot value. Okay, so what I'm trying to say is, see here, this is the definition of each node in the tree. It has a dot value, but this value will only be existing if the child is not none. Okay, so you should not do a dot none dot value of a child which is none. Okay, that is the basic idea. If you do that, you will get error. You have to avoid such a case. Okay, so how to do that? See, the best approach which I am going to tell you is that trying to convert each of the trees into a canonical form. What is a canonical form? See, you can define anything of your own. See, canonical basically means we are setting the standards. Okay, so that if I have a tree, if I set that tree to a canonical standard, that means if whatever with the flip equivalence of it, okay, in whichever way you can get the flip equivalence, all of them will come to the same canonical form. That is the basic idea. Let's see how it works. So there are few standards here. What is the standard? See, if the node has a single child, okay, it should always be towards the left. That is the first rule here, okay. For example, in this case, 3 has a single child, it is towards its left. That is the basic idea, okay. Whenever a node has a single child, it should be towards its left. What is the other rule? Other rule is that child, if the particular node has two, childs, then what will happen? The child with the higher value will be towards the left, okay, as simple as that. It does it make sense? That's how it is, okay. If there is single child, it should be towards the left. If there are two childs, the child with the higher value should be towards the left, okay. So this is how I'm going to convert each of the rules given to me into a canonical form, okay. For this, I'm declaring a function called the canonical form, okay. Yeah, this is the function. Here, what I'm doing, I'm doing a simple, I'm going through each node, okay. I am taking its left and right, childs. Then I'm applying these algorithms, okay. I'm doing the swapping if needed, okay. This is how I'm doing it, and then I will be calling this particular function for the root 1, root 2, that is for the nodes given to me. That is, I'm converting both the rules given to me, there is both the trees given to me, into its canonical forms, and then I will start the comparison, okay. I hope it makes sense to you. See, through this approach, what we are trying to do is we are trying to bring them to a common, common scale, okay, where we can compare them, right. We are trying to bring them to a common, ground, so that they can be compared, okay. That is the only idea. So what I'm doing it here in the canonical form, if the root is null, simply return it, okay. Take the root dot left, I am calling it as a left for easy reference. Similarly, take the root dot right, I am calling it as a right for easy reference. That is the left subtree and the right subtree root, okay. This is the root of the left subtree, this is the root of the right subtree, okay. If left is none and right is none, that is if this particular parent doesn't have any child, okay, in that case simply return, because here I don't have to do anything here, okay. This will remain as it is only. The other case is when the root, that is the current that we are in, has at least one children, okay. There has at least one children. Remember, if I am, this particular condition is not getting resolved and I'm coming to this condition, remember it is else if, okay, it is else if I'm coming to this condition and it is getting satisfied, this basically means I have a single child, okay. This basically means I have a single child. In that case, okay, what I have to do, so what, whichever is a single child, it has to be towards the left, okay. If it is already in the left, then I don't have to do anything. If it is not in the left already, then I have to make it. So what I have to do, I will check if the right is not none, okay. That is, the child is at the right. So what I have to do, root dot left is equal to right, that is C. The right, what is right? Right is basically the root of the right subtree. So now I am assigning it to left, okay. Root dot left is equal to the right subtree, and root dot right is equal to the left subtree, which is none, okay. This will be none in this case, okay. This will be none. Instead of left, you can also write none here, okay. That is fine. You're doing it. Remember, if the child is already towards the left, I don't do anything, okay. This if condition will not enter, as simple as that, okay. This else if also I have discussed. Now comes to this part, okay. If the current node that we are discussing has two, childs, and obviously if there are two childs, if you see the constraints here, no, you'll get to know that. See the constraints here, they are saying all the, nodes are of unique value. That is, one, both the child cannot have same value, as simple as that, right. They cannot have same value. So what I have to do, see here what I'm doing, the child with the right higher value should be towards the left, okay. So what I'm doing, yeah, so I'm comparing it here basically. If the left value, that is the left child's value, is smaller than the right child's value, okay. So what I'm discussing here, the left child must have the higher value, okay. So the right child currently has the higher value, I will be taking it towards the left, okay. Right child should be allotted to the left, pointer of the current node. Similarly, the left subtree should be made the right child of the current root node, that is current parent. Then from here the function is completed, okay. Yeah, this is all it is. After that, I am, recursively calling it towards its left subtree. That is the DFS approach, right? Once the current node is processed, go to towards processing one of its root, okay. Go towards the depth, okay, of one of its root. That is, I am starting with the root dot left here, okay. I'm calling the same function for its root dot left. I'm calling the same function for its root dot right, okay. With this, I am completed with this particular function, okay. Now for the inputs given to me, that is root 1 and this is the root, okay. I am calling the same functions. Convert to canonical form root 1, convert to canonical form root 2. Once it is done, yeah, once I am done with this, both the roots are converted to their canonical form. Now I can start the comparison. I am taking the answer with the default value of true, okay. When if I see some discrepancies, I will be making it as a false, and then finally I will be returning the answer here, okay, as you can see here, okay. Now I am defining another function. So what I'm doing, I'm going to compare the two roots using a DFS approach, okay. I will going toward the depth of one particular child, and I will be comparing their nodes if they're equivalent or not, okay. So what I'm doing here, I'm calling the function DFS of root 1 comma root 2. That is, I'm passing both the roots. This particular function takes both the roots and does the comparison, okay. So what I'm doing, yeah, remember friends, whenever you are declaring a function, okay, and you are trying to access a value which is declared outside, that is, this particular value is declared outside, but I am going to, use it inside the function, then you have to make it, you have to declare it as a non-local. Otherwise, what Python does is that it will create a copy of this and start using it here. But what will happen is the value will not be updated to the value which is present outside. Okay, both of them will not be in sync. This answer will not be in sync with the answer that you are using inside the function. Okay, so whenever you are in a scope of a function and you are trying to use a value which is declared outside, try to declare it as a non-local. Okay, as simple as that. Especially in lead code, this will always work. In other cases, it may not work because see, here the answer itself is a function. Okay, inside a function we're declaring another function. That's why this is needed to be declared as a non-local. This is one important concept. If you have been watching my video, I'm damn sure you will be knowing about it. Yeah. So what I'm doing, if both the roots are none, that is both are matching in that case. Okay, simply return. I don't have to do any further processing here. Return it, return back. Okay, because see, if the roots are none, obviously they will not have any left or right child, so I did not call it recursively on them. Okay, so I'm simply returning it. Okay, other than that, if the root one is none but root two is not none, in that case they are not possible. That is, both of them are not the same. Okay, that is, see, this is what the question is, right? Given the root true, if the two are flip equivalent, see, if we see, after converting them to canonical form, if something like this happens, that means they are not flip equivalent of each other. Even after flipping them, will not be able to get the same tree back. Okay, so that's why the answer will be made false and I am returning. Okay, I don't have to do any further processing here. I will be returning it as it is. Okay, I'm returning from here. Okay, if root is none but the other root is not none, same condition here in the reverse way. If root one is not none but the root two is none. Okay, root two is none, again it is not possible to be flip equivalent. If this condition is true, then make the answer as false and return. Okay, what is the other case? If their values are not seen, here we are saying if either one of them is none but the other one is not none here. Okay, those cases are over now. When I'm coming to this part, that means both the roots are not none, that is both of them will have a value. Then I have to check whether the values are same or not. If the values are not matching, again make the answer as false and return. If I'm able to come to this part, that means at least at the root level, that is at the parent level, everything is matching. Okay, so what I have to do, I have to do the same comparison for the childs. So it is called the same function for its both, that is for the left subtree of the root 1 and the same left subtree of the root 2. Similarly call the same function for the comparison for the right subtree of the root 1 and the right subtree of the root 2. That is, see, this is a basic DFS approach. That's why see the name, it's a DFS algorithm. I'm doing the DFS algorithm, but at the each each parent level I am doing the comparisons as well. Okay, this part is extra here. Okay, these are the comparison part, this is extra here. Otherwise this whole function is a basic DFS function. Okay, as it is. Here I'm doing the function call to this. Okay, and this is the function, DFS function. Only extra thing here is I'm doing the comparisons which are here. These are the extra comparison that I'm doing. At each root level, they should happen. That's why after the comparison is done at a particular root, all the same function for the left and the right subtrees. Okay, so that the comparison happens for them also. After that, I'm returning the answer. Okay, by default the answer is true, but if any of these cases becomes true, okay, the answer will be made as false. Okay, so let me quickly run this and show you. If you see, all the test cases are getting cleared. Okay, yeah, all the test cases are getting cleared here. Okay, so yeah, friend, that was all for today. And one more thing, like if you are really good in solving questions, and if you are aiming for some goodies in the lead code, then you can also contribute test cases, and this will get you some more extra points which you can use to get goodies from lead code. Okay, similarly, you need around 6,000 points for a t-shirt and something like that. Okay, 5,400 for a cap, and you can see the rewards when you will get to know that. So if you are planning for something like that, and if you're near to those points, then maybe you can start contributing test cases to increase your points. This will also be a good point to mention in your resume that you are contributing test cases or questions to LeetCode. Okay, this will be definitely getting you some attention even in your coding interviews. So yeah, that was all for today. If you like my efforts, please do subscribe to my channel. This really gives a lot of motivation. Thank you. See you tomorrow.